Good morning, everyone, and thank you for being here today. I'm pleased to welcome you to this presentation on the limit of qualification, or LOQ, criteria in analytical method validation. My name is Dr. S.K. Singh, and I hold a PhD in this field. Today, we will explore the key aspects of LOQ, why it matters, and how it fits into the broader process of validating analytical methods. We'll cover the essential criteria, practical considerations, and best practices. So, let's get started and deepen our understanding of this important topic. Let's start by exploring what we mean by method validation. It's a crucial part of ensuring that our analytical methods are reliable and accurate. When we talk about validation parameters, we're referring to specific criteria outlined in USP 1225. These include accuracy, which tells us how close our measurements are to the true value; precision, which reflects the consistency of our results; specificity, to ensure our method can distinguish the analyte from other components; linearity, which confirms our method's response is proportional across a range of concentrations; LOD, or limit of detection, indicating the smallest amount we can reliably detect; LOQ, or limit of quantification, which is the lowest amount we can quantify with acceptable precision and accuracy; range, representing the interval over which our method is reliable; and finally, robustness, which tests how resilient our method is to small variations in conditions. All these validation parameters work together to ensure that our analytical methods are dependable. When properly validated, they guarantee reliability, accuracy, precision, and sensitivity. This foundation is essential for producing trustworthy data, whether we're developing new methods or validating existing ones. So, understanding and applying these parameters is key to maintaining high standards in our analytical work. Let's take a closer look at the definition of LOQ, or the limit of quantitation, according to USP. The LOQ refers to the lowest amount of an analyte in a sample that we can measure reliably, with suitable precision and accuracy. In other words, it's the smallest quantity we can quantify confidently, without too much variability or error. It's important to understand how LOQ differs from LOD, or the limit of detection. While LOQ is about quantifying the analyte, the LOD is simply about detecting its presence. So, the LOD tells us if the analyte is there at all, even if we can't measure it precisely. In practical terms, if we detect an analyte at or above the LOQ, we can confidently state how much is present. But if it's only above the LOD, we know it's there, yet we can't accurately determine the amount. This distinction is crucial in ensuring the reliability of our analytical results and maintaining quality in our testing processes. Let's talk about the different methods for determining the limit of quantitation, or LOQ, according to USP. There are three main approaches to this. First, we have visual evaluation, which is a more straightforward qualitative method where you assess the point at which the analyte can be reliably detected by eye. Then there's the signal-to-noise, or SN method, which involves measuring the ratio of the signal from the analyte to the background noise. Typically, a ratio of 10, 1 is considered acceptable for LOQ. Lastly, we have the standard deviation and slope method, which uses statistical calculations based on multiple measurements to determine the LOQ more precisely. Now, understanding when LOQ is required is also crucial. It's necessary for methods that analyze impurities, related substances, degradation products, and residual solvents. These are often present at very low levels, so accurate quantification at these trace levels is essential for ensuring product safety and compliance. On the other hand, LOQ is not usually needed for assay methods, unless there's a specific justification. For example, if the main purpose is to determine the potency of a compound at higher concentrations, LOQ might not be as critical. So, in the context of overall method validation, knowing when and how to determine LOQ helps us ensure that our analytical methods are both reliable and appropriate for the specific substances we're analyzing. Let's take a closer look at Method 1, signal-to-noise ratio. This approach focuses on measuring how strong the actual signal is compared to the background noise. Essentially, A higher ratio indicates a clearer, more distinguishable signal, which is crucial for accurate analysis. When we talk about signal-to-noise ratio, we're highlighting the importance of filtering out the noise to improve data quality. This method is often used because it provides a straightforward way to assess the reliability of the data we're working with. In the context of our overall presentation, this method helps us understand how well our system can detect meaningful signals amid the inevitable background interference. Improving this ratio means better detection accuracy and more dependable results. So, by focusing on the signal-to-noise ratio, we're essentially optimizing our ability to extract valuable information from noisy environments, which is a key step toward more precise measurements and successful applications. Let's take a closer look at method 2, the formula method, which involves using sigma. And as this approach is particularly useful when we want a straightforward calculation of variability or spread within our data. Essentially, sigma represents the standard deviation, which measures how much the data points deviate from the mean on average. S, on the other hand, is typically used for the sample standard deviation, especially when we're working with a subset of data. The key here is that this method allows us to quantify variability in a clear, mathematical way, making it easier to compare different datasets or assess the consistency of a process. It ties into our overall theme of understanding data reliability and quality. By applying these formulas correctly, we gain valuable insights into the stability and predictability of our processes or measurements. So, in summary, the formula method with sigma and S provides a precise, quantitative way to analyze data variability, which is fundamental for effective decision-making and quality control. Now, let's talk about how we determine sigma, or the standard deviation, which is a key parameter in our analysis. Sigma can be obtained in a couple of ways. One common method is by looking at the standard deviation of blank responses, which are the responses when no analyte is present. Alternatively, we can use the SD of the y-intercepts from regression lines, especially when we're working with calibration curves. Let's look at an example with some blank area values: 120, 135, 140, 125, and 130. Calculating the mean of these values gives us 130. From these, the standard deviation, or sigma, comes out to approximately 8.37. This sigma value is particularly important because we use it in calculating the limit of quantification, or LOQ. Essentially, understanding and accurately determining sigma helps us define the smallest amount of analyte we can reliably measure. So, whether we're using the variability in blank responses or the regression intercepts, the goal is to get an accurate sigma to ensure our method's precision and reliability. Now, let's move on to slide 8, which focuses on the verification of LOQ, or the limit of quantification, specifically looking at precision at this level. This is a crucial step because it helps us ensure that our method can reliably measure small amounts of analyte. When we talk about precision at the LOQ, we're essentially testing how consistent our results are when measuring samples at the lowest quantifiable level. It's important because if our method isn't precise at the LOQ, then the data we generate could be unreliable or inconsistent. During this process, we typically run multiple replicates, say 5 or 6, and then assess how close those results are to each other. The goal is to demonstrate that, even at the lowest detectable levels, our method produces reproducible and accurate measurements. This verification step ties back to our overall theme of method validation, ensuring that our analytical process is both reliable and fit for purpose. Ultimately, confirming precision at the LOQ gives us confidence that our results are trustworthy, even when working with very small quantities of the analyte. Let's talk about accuracy at the LOQ level. When we refer to LOQ, or limit of quantification, we're talking about the smallest amount of a substance that we can reliably measure with confidence. Ensuring accuracy at this level is crucial because it directly impacts the reliability of our results, especially when working with very low concentrations. It's important to recognize that as we approach the LOQ, maintaining accuracy becomes more challenging, but it's essential for the integrity of our data. We need to carefully validate our methods to make sure they can accurately detect and quantify these low levels without bias or error. In the context of our overall quality assurance, accuracy at the LOQ ensures that even the tiniest amounts are correctly identified, which is vital for compliance, safety, and scientific credibility. So, paying close attention to accuracy at this level helps us uphold the highest standards across our testing processes. All right, let's talk about the acceptance criteria for the limit of quantification, or LOQ. First, the general criteria include a signal-to-noise ratio of approximately 10:1, which helps ensure that the detected signal is reliably distinguishable from the background noise. Next, the relative standard deviation, or %RSD, should typically be less than or equal to 10%, especially when we're dealing with impurities, to confirm the precision of the measurement. Recovery rates should fall within the range of 80 to 120%, indicating that our method accurately captures the analyte without significant loss or overestimation. Additionally, the peak corresponding to the analyte needs to be clearly distinguishable from other signals, ensuring that our identification is unambiguous. It's important to remember that these criteria can vary depending on the specific Standard Operating Procedure, or SOP, so always check the relevant guidelines. Overall, these criteria help us maintain consistency, accuracy, and reliability in our analytical methods, which is essential for quality control and compliance. Now, let's take a closer look at the difference between LOD and LOQ. These two terms often come up in analytical methods, and understanding them is crucial for accurate measurements. LOD, or limit of detection, is essentially the smallest amount of a substance that we can confidently identify as present, but not necessarily quantify precisely. It's like saying, yes, I see it, but I can't say exactly how much. On the other hand, LOQ, or limit of quantification, is the smallest amount that we can measure with acceptable accuracy and precision. Think of LOQ as the point where our measurements are not just detectable, but also reliable for reporting. Recognizing this distinction helps ensure we interpret our data correctly and maintain the integrity of our analysis. It ties back to our overall goal of achieving accurate, dependable results in our testing processes. In conclusion, LOQ, or the lowest quantifiable amount of analyte, is a critical concept in analytical chemistry. It essentially tells us the smallest amount of a substance that we can reliably measure with confidence. To do this effectively, we need to demonstrate that our method produces acceptable levels of precision and accuracy, ensuring our results are both consistent and correct. There are a couple of common ways to determine the LOQ. One is the signal-to-noise, or SN method, which compares the analyte signal to the background noise. The other is the 10 sigma over S formula, which is a more statistical approach. Both methods help us establish a robust detection limit. Understanding and accurately determining LOQ is especially important in impurity and trace analysis, where we're often dealing with very small amounts of substances. It's a key part of method validation, particularly under the USB 1225 guidelines, which set the standards for ensuring our analytical methods are reliable and fit for purpose. So, in essence, mastering LOQ helps us confidently measure even the tiniest quantities, which is vital for quality control and regulatory compliance in our work. For further support, please feel free to contact us. We're here to help you with any questions or additional information you might need. Remember, your success is our priority. Thank you so much for your time and attention today. We appreciate your engagement and look forward to assisting you further.